You ever hit enter on a search and just wonder how a whole web page appears, like magic? Well, behind that split second is this epic hidden journey. A tiny digital hero is literally racing across the globe in milliseconds. So let's dive into this hidden world and follow the incredible life of a single network packet.
All right, here's our game plan for this packet's adventure. We're going to trace its path through 6 key stages. We'll start from its creation, right there on your computer, follow it all the way to its destination, and then watch it make the trip all the way back home.
Okay, first things first, let's get one thing straight. The internet isn't some fuzzy, magical cloud. It helps to think of it as the world's fastest, most efficient postal service, a very real, physical network of wires and routers. And the hero of our story, the little digital letter doing all the work, is the packet.
So what exactly is a packet? Well, your computer doesn't send a whole web page or a giant file all at once. That would be super inefficient. Instead, it breaks it down into thousands of these small, manageable chunks. Each packet is like a tiny digital envelope. Inside, you've got a piece of the data, the letter, and on the outside, a header, which is basically the shipping label, telling it exactly where to go. And the reason for this is just brilliant. It makes the whole system incredibly tough. If one packet gets lost along the way, no big deal. Only that tiny piece needs to be resent, not the whole file.
Now, before our packet can even think about starting its journey, it has to be prepared. This process has a fancy name, encapsulation. But really, just think of it like meticulously wrapping a present, adding multiple layers of labels where every single layer has a very specific job to do.
What's so fascinating is how each layer just adds a new wrapper. First up, DNS acts like the internet's giant address book to find the actual IP address for, say, google.com. Then the application layer writes the actual request. Next, the transport layer adds its information using TCP, and this part is absolutely crucial. It's like choosing certified mail with a tracking number. TCP makes sure every single packet arrives safely and can be put back together in the right order. It's all about reliability. Finally, the network layer slaps on the main address label, the source and destination IPs, and the data link layer adds a local address just for the very next stop on the journey.
Now, you might have heard of a 7-layer OSI model for all this, and you're not wrong. That's kind of the detailed, theoretical blueprint. But in the real world, the internet we use every day actually runs on this more practical, streamlined 4-layer TCP/IP model you see here. It's the same core idea, just built for real-world speed and efficiency.
Okay, our packet is all packed up and ready to go. But its first step isn't some massive leap across the globe. No, it's just a tiny hop across your room. Seriously, think of it like walking a letter from your desk to the mailbox at the end of your driveway. That's the journey from your computer to your Wi-Fi router.
For this short, local trip, that big global IP address is total overkill. Instead, devices on the same network use something called a MAC address. The best way to think about it is like this. An IP address is your full home address, usable from anywhere in the world. A MAC address, that's just the name on your mailbox, which only matters to the mail carrier who's on your specific street.
So how does your computer find the router's local mailbox name? It's pretty clever, actually. It basically just shouts out a question to everyone on the local network using a protocol called ARP. It's asking, hey, who has the router's IP address? I need your MAC address. The router hears this, replies with its MAC address, and boom! Just like that, the packet gets its local address label and gets sent on its way.
And now the real adventure begins. The second our packet hits your router, it leaves the quiet little local neighborhood and merges onto the vast, chaotic superhighway of the internet. This is where the long-distance magic really happens. The key players out here on this highway are the routers. Every router our packet meets is like a massive postal sorting facility. It has one job, and one job only. Look at the destination IP address on the packet and make a split-second decision about the best next step to get this thing closer to where it's going.
And this simple process just repeats over and over again, sometimes dozens of times for a single packet. It arrives, the router reads the IP address, it quickly checks its internal map, which is called a routing table, and then forwards the packet to the next best router in the chain. Each one of those jumps is called a hop.
But wait, what happens if a packet gets lost? Stuck in some kind of routing loop? Well, to stop that from happening, every packet is born with a little countdown timer called time to live, or TTL. A common starting value is 64, and at every single router it hops to, this number gets decreased by 1. If that counter ever hits 0, the packet is just destroyed. It's a brilliant safety feature that prevents these ghost packets from just circling the internet forever.
After hopping across countries, maybe even under oceans, our heroic little packet finally arrives at the destination server. But the job's not quite done. The server can't read the message yet. First, it has to carefully unwrap all those layers we added way back at the beginning, and this reverse process is called decapsulation.
And this is where you can really see the beautiful symmetry of the whole system. Each layer is peeled back in the exact reverse order it was put on. The local MAC address label comes off first, then the main IP address label, then the special TCP instructions are removed, until finally, the original data, or HTTP request, is revealed and handed off to the web server.
But hold on, you didn't just want to send a request, you wanted to actually see the web page, right? Getting your packet there was only half the battle. Now the server has to package up that entire web page into thousands of new packets and send them all the way back to you, following that same incredible journey, just in reverse.
So let's just recap this whole wild ride. Your request gets sent, it hops all over the internet, the server gets it, processes it, and then sends a response all the way back. The truly mind-boggling part is the speed. This entire round trip can happen in as little as 150 milliseconds. I mean, that is faster than the blink of an eye. It's absolutely incredible when you stop to think about it.
So, the real takeaway here is this. What feels like instant magic is actually an astonishingly complex but beautiful, elegant system. It's a dance of protocols and layers and hardware all working together in perfect harmony, all governed by these strict rules that allow for this seamless, global communication. And if one path goes down, the routers are smart enough to just find another one. That's the beauty of it all. And that really leaves us with a final and pretty important question. The fundamental principles of this system we just walked through were designed over half a century ago. Now, it is scaled in ways its creators could have never, ever imagined. But as we're now entering this era of AI, the Internet of Things, and just astronomical data demands, you have to ask, is this incredible system ready for the challenges of the next 50 years?